This lecture is part of a series of lectures for Rad229, MRI signals and sequences offered in the Department of Radiology at Stanford University. The third lecture is broken into two parts. Lecture-03A covers the Bloch equation in matrix form and matrix operations for nutation, relaxation, and precession. The learning objectives are to write the Bloch equation in matrix form, to write matrix operations for relaxation, nutation, and precession, to combine successive matrix operations, and to explain how to transform to other matrix formulations. So let's start with the basic Bloch equation. As you have seen, this is a standard right-handed cross product. The change in magnetization over time is expressed as the cross product of the magnetization with the gyromagnetic ratio times the applied magnetic field. We subtract off this term that corresponds to T2 relaxation of the transverse magnetization, and we add this term that corresponds to longitudinal relaxation. So starting again with the Bloch equation as shown here, we see that if we define the m as an m vector with components mx, my, and mz, and we usually set m0, the equilibrium magnetization, to 1, if we do this, we can actually write the Bloch equation in this matrix form here, where the change in the magnetization vector is written as shown here. And here we've combined the effects of rotation due to an applied magnetic field B, as well as relaxation. Although the Bloch equation is difficult to solve for general cases, there are specific cases that we can solve for. In the case where all we have is relaxation, the solution is given as shown here. Over some period tau, the magnetization is this attenuation matrix, often called A, multiplied by itself, plus the recovery term that corresponds to longitudinal recovery, and this is often called a B vector here. Notice that we often use this shorthand. You'll see this in many cases where people are simulating sequences using these numbers E1 and E2 as expressions. So if we have this information, we can already move quickly to numerical simulations here. So this is an example here where we're calculating the relaxation over a period of half a second with a t1 of half a second, a t2 of 0.1 seconds, and the 1 indicates how we express the answer, which is to concatenate the A and the B here. What you see here is we have relaxation over a total of 5 t2 times, so the attenuation of the transverse magnetization is almost to 0. And you notice here that we basically have e to the minus 1 in the bottom right term here, and we see that we have a considerable recovery over a full t1 time. Now we can animate this by simply applying this propagation repeatedly with a small tau, and you can see that basically starting with the magnetization along mx, the relaxation will take the magnetization back to the equilibrium level. Now I should state that this animation does not correspond to the T1 and T2 shown in the relax.m example here. I should also emphasize that the .m files here are all given on the class GitHub in the MATLAB directory. So let's do a quick example here. If we have a T1 of 1 second and a T2 of half a second, what are the relaxation matrix, that is A matrix, diagonal elements for a tau time of half a second? So when you see these questions, please think about the answers before you even show the multiple choice answers, and then you can think about the correct answer. So here are the options. And the correct answer here is, if you just think about it, E1 is always greater than E2 because T1 is always greater than T2. So this eliminates answer B, for example, and answer C. Second, e to the minus 1 is about 0.37. So that points to answer A, because we have relaxation here over exactly 1 T2 time. So it's good to remember these numbers and start to get a feel for what e to the minus 1 is in e to the minus a half, because you're often going to be thinking in these terms of how much attenuation you have from relaxation. Okay, now let's look at RF. Now, we can also express the effect of an RF rotation or nutation using a matrix form. For a flip angle alpha, the rotations about x or y are shown here. Notice these are simple rotation matrices. The axis of rotation is obvious here. You see where the 1 is with zeros across and zeros down in the matrix, and this indicates the rotation is about mx. And down here, the orange matrix shows a rotation about my. Now the rotation angle is the gyromagnetic ratio times the B1 field times the duration of the RF pulse, and in this case alpha is in radians. Rotations here are left-handed. This also could be achieved by negating gamma with a right-handed rotation. So here's an animation. Notice this is a rotation of negative alpha about y, or equivalently of alpha about negative y. And this brings the magnetization down to be along mx. We can also apply simple functions in MATLAB here that give you these rotation matrices for any angle. So this brings us to another question here. The question is to describe the left-handed rotation that is given by this matrix here. So here are your possible answers here. Okay, and the correct answer is B. The rotation is about the my axis, and you can see that from the position of the 1 and zeros. It's a small rotation because the cosine is along the diagonal, and the cosine is larger than the sine here, so that should show you that it's 30 degrees and not 60 degrees. Of course, you can calculate this out, and if you know your sines and cosines, you can tell that this is a 30-degree rotation. So another case that we often have is when the B1 axis is actually somewhere in the transverse plane, but not necessarily along x or y. And in this case, we can also say that the RF has some other phase to it. In this case, the matrix becomes quite a bit more complicated. You have this expression here, where this angle phi is the azimuth angle, which is basically the angle of the rotation axis, and alpha is still the rotation angle here. Notice that this matrix is actually achieved by simply taking the magnetization, rotating it back so that that blue line is actually along the x-axis, doing a rotation around the x-axis, and then rotating the magnetization back. And in some cases, we're actually going to need completely arbitrary rotation axes here. So this is a case where we might combine the B1 field with actually some off-resonance precession or gradient-induced precession, and we'll see this later. In this case, the expression is actually very complicated, so I'm not going to write that here. But what we can show you is, again, given a rotation angle of alpha, given an elevation angle theta, and an azimuthal angle phi, that basically you can write this rotation, you can break it up into 5 different rotations and do this quite easily. And numerically you could calculate this rotation matrix, and again it would be a 3x3 rotation matrix. So when we have rotations due to a gradient or due to B0 effects, or a change in B0, which could be induced by off-resonance, again we have a rotation matrix, and this time it's about the MZ axis. So now you see the 1 is in the bottom right of this matrix, and the zeros are along the same row in the same column. And again you have cosines and sines here. Now here, remember that the rotation angle now here is shown to be basically the gyromagnetic ratio times the dot product of the gradient with position plus any delta B0 term times the duration here, tau. So this delta B0 term could be from a chemical shift frequency difference or some other off-resonance term. Again, the rotation angle here will be in radians. So this is just an example of precession from one spin here. So if we have one spin, it's precessing around the z-axis. Now if we apply a gradient, there are many different ways to illustrate this, but basically at different positions, the spins are seeing different amounts of precession, and this video is just repeating here. Okay, so now we've put this all together, you can actually simulate things like nutation followed by precession and relaxation. You can also do this in the lab view or the rotating view simply by adding an additional term, B0 rotation, as you've seen in the previous lectures here. So you can do these different simulations by simply combining these operations, as we'll see in examples shortly. Now you should really try to have fun with MRI, and this is something that I've longed to achieve for a while, and finally achieved this video. So here you can see that my son's gloved hand here is the tip of the M vector as we excite the magnetization. Notably on the right, we're in the rotating frame, which means I'm actually filming it on top of this playground merry-go-round. This brings us to another question. So now we're asking, what operations does this matrix simulate? So here are the possible options here. Okay, and the correct answer here is E, none of these. And the reason for this is that this is a rotation and transverse relaxation. Notice that the cosine and sine terms here are too small because there's some attenuation due to T2 relaxation here. So the rotation here is about 45 degrees, which you should see here based on the fact that the cosine and sine are the same. It's actually a minus 45 degree rotation about mz. But there's also a scaling here based on relaxation. But also notice that there's no longitudinal relaxation, so this would be equivalent to an infinite T1. Okay, so a final operation that we can very easily simulate with a matrix is what we call perfect spoiling. Now this will come up in future lectures, but this is where we can explicitly set the transverse magnetization to 0. And this will apply to sequences where we neglect the magnetization at the end of the TR and assume that transverse relaxation has brought this transverse magnetization completely to 0. And this matrix, all we do is we simply zero out the transverse magnetization here. So now that we have these matrix operations, so now that we've seen these operations, we can actually propagate magnetization through multiple sequence blocks. We've already shown that rotations and relaxation can be written in this form. M prime is equal to A times M plus B, where A is a 3×3 matrix, M is a 3×1 vector, and B is a 3×1 vector. So if we assume that M0 here is the starting magnetization, not the equilibrium magnetization, we can write through one step that M1 is A1 times M0 plus B1. We can next propagate through a next step that M2 is A2 times M1 plus B2. Now we can propagate through as many steps as we like simply by multiplying the A matrices and summing the B vectors after multiplying by all successive A matrices. And this takes the form that looks like this for this simple example, where the overall A matrix is the product of A2 and A1, and the overall B vector is A2B1 plus B2. So we can write this in this form here, where A is simply the product. Notice that these are in reverse order. And B is the sum of the product of successive A matrices in reverse order multiplied by the B vectors. So next we'll also talk about an alternative method of showing the matrix form of all of these operations. So what you can do here with a 4×4 solution is you can eliminate the additive B vector. And you do this by making the magnetization a 4x1 vector here. And the last element is always 1. And what you notice is all of the operations will retain a 1 in the last element of this matrix. And there's a very simple relationship between what we've already seen, which is the 3x3 representation, and the 4x4 representation. And it's shown here. So in this sort of block diagonal matrix here, you can see that the last element will always be 1 because it simply propagates itself. But what we've done here is we've combined the 3x3A matrix and the B vector into the top 3 rows of this 4x4 matrix here. What this does for us is now relaxation is just a simple multiplication term. So let's look at relaxation. If we go from the 3x3 to the 4x4 formulation, what you see, again, we use the shorthand with E1 and E2. You see that the magnetization after the relaxation here is the A matrix times M plus B. But if we write this in the 4x4 formulation, what you see here, again, the block diagonal form here, more or less, is that we have the 3x3A matrix here. We have a 1 in the bottom right, and then the last, these rightmost and top 3 elements here are the original B vector here. So quite a simple transformation here. Notice that we could easily do the reverse transformation of any of these operations simply by extracting the A matrix and the B vector from the 4x4 representation. Of course, we can do rotations just as easily here. And with rotations, there's no B0, so this matrix truly is block diagonal here. So let's look at another example here. If you do operations in order represented by A1, A2, A3, and A4 in the 4x4 homogeneous representation, what is the overall operation here? So what is the overall propagated A matrix here? So here are your possible choices here. And we've written this in as the magnetization afterwards and the magnetization before, and a product of A matrices, and in some cases the addition of a vector. So the correct answer is B, and remember that the matrices are combined in reverse order so that they multiply M in increasing order. There's no B vector in the 4x4 system. So another very useful matrix formulation is to use a complex magnetization vector. So far we've used real valued vectors, as shown at right here in blue. But there are some advantages to a complex vector. First of all, the complex signal is simply the first row, so that may be attractive. Second, it's easy to apply gradient-induced phase because it's a simple multiplication, and we'll see this in some examples. You can express rotation and relaxation fairly easily. And lastly, there's a simple transformation. So if we look at this transformation at the bottom here, we can easily see that going from the blue to the yellow here, this transformation matrix T shown here will easily achieve that transformation, and we can simply invert this transformation matrix, or we can actually look at and easily generate the inverse of the transformation matrix as well. So now we can use this simple transformation matrix T. If we do this, relaxation is unchanged. It's a block diagonal formulation, so this doesn't change between the real valued and the complex valued formulations. The rotations are just transformed using this transformation matrix T as shown here. And if we can actually take the rotation matrix about an arbitrary axis in the mx, my plane, and this matrix takes on this form, which we will actually see again later on. As I said previously, one of the advantages of the complex format is that gradients can be applied relatively easily. So what we can do is we can make the complex matrix, complex vector, which I'll call MC, 3 by n, so that we can simulate n spins at different positions here. Remember, the 3 by 3 multiplications will work just fine if we spread out our magnetization vector to include multiple, essentially multiple pixels or multiple spins, whatever you'd prefer. So here is some MATLAB code to show you how you might apply gradients. So I'll read through this and explain it. So here we have a range of positions or z locations from -1 to 1. We initialize the magnetization to be along mx here. Now we can take a phase twist here, and we can basically make this phase twist a simple linear phase. So it's e to the power of I times pi times z. And this will give you one phase across the range of positions that we have. Now we can just extend this phase multiplier and put it in the coordinates of the complex magnetization vector. So we multiply by the phase and the conjugate of the phase, and then we can actually multiply the last row by 0 here. We probably want to multiply this by 1 if we actually have longitudinal magnetization. And then we can simply use these functions mc2mr and mr2mc, which just apply those transformations between real and complex matrices. So we have a real valued m here, and we've transformed it to complex. We've multiplied by the linear phase, and we've transformed it back to a real value. And now we can go ahead and plot that twist. And if we do this, lo and behold, we see this nice view of one cycle of phase twist. Okay, and we've simulated this relatively compactly, and actually would be much more compact if we just had set up the magnetization in the complex system to begin with. So we will see this a lot later as well. So another question here. If the real value... So here's another question. If the real valued m vector as shown, what is the complex vector? And notice we often write these vectors horizontally with a transpose operation. So here are your possible solutions. And here is the correct answer, D here. And this is simply seen by the fact that the first element of the complex representation is the sum of mx plus I times my. And in this case, my is negative, so answer D is correct. Okay, so this brings us to the end of this lecture, really. But what I just want to highlight is that in our course Rad229, most of the functions and examples that we have are available in GitHub. So there's a MATLAB folder, which has general functions, and there's a lectures subfolder here, which has lecture examples that we will go through in class. So you can go to this GitHub anytime, and this is linked off the main class page. If you want to make videos, it's kind of fun. If you want to make these look a little prettier, you can use the arrow3D function. And I recommend that you download this straight from MathWorks in case they change this code. It's a very simple function, but it will make these nicer arrows. Now there are other options to do arrows as well in other packages, but this one is quite simple. In terms of animations, it's nice to be able to shoot multiple frames from a MATLAB functions and save these easily to make little videos, such as what you see here. So we have a very simple function called save frame, and this is also in the MATLAB folder here. And you just basically set two variables, and then every time you plot something, you can capture a frame, and it numbers these automatically so that you can combine these to make some kind of a video. So to summarize this lecture, the magnetization M is modeled as a... So to summarize this lecture, the magnetization can be modeled as a 3 by 1 vector. Remember, you can extend this horizontally to model multiple spins or multiple locations. The Bloch equation and its solutions can be written in a matrix form. Rotations are simple multiplications, and relaxation is a multiplication with an additive term. The 4x4 matrix formulation eliminates this additive term, and a complex representation eases the application of gradients. So in the next lecture, we will address how do we use these matrix operations to simulate sequences.